Here we have to do some application to the gamma decay. You know, gamma decay is the transition between one of the excited state to another lower state. It can be to a lower state or to the ground state. First of all, I want to characterize the transition or the radiation. The radiation, it can be, first of all, we have to find the multipolarity. You know, it can be dipole if L equals to 1. It can be quadrupole, octupole, and so on. This is a multipolarity of any transition, and we have to precise the nature of the transition. It can be electric or magnetic. We can say E or M. For each transition, we have two possibilities. We have E, for example, for L equals to 1. We have the possibility to have an electric dipole transition E1, or we can have a magnetic dipole transition M1. For L equals to 2, we have electric quadrupole transition E2 or magnetic quadrupole transition M2 and so on. So this is about the nature and the definition of any transition. We have to find its multipolarity and the nature. The second point here, you know, for any excited state or for any state, we have the nuclear spin, J or I. We have a J initial and we have a J final. To find the value of L, we need to calculate its range. It will be between the Ji minus J final absolute value and the Ji plus J final absolute value. And we can calculate L, and L must have the minimum value of L equals to 1. Okay, L must be equals or greater than 1. Okay, so this is about the value of L. About how can we precise if the transition is electric or magnetic? We have to study the parity of the excited states of the initial state and the final state. Okay, in the case of electric transition, EL, the parity, we can say here, parity initial equals to -1 power L parity final. In the case of magnetic transition, we can say parity initial equals to -1 power L plus 1 P final. We can say P initial equals to -1 power L P final, or P final equals to -1 power L P initial. It's the same for E and L. Okay. So this is the condition to have an electric transition, and this is the condition to have a magnetic transition. Okay, let's go to the examples. First of all, I give you a simple example. I give you the transition between the initial state and the final state. We have only two states, from this one to this one. We have gamma. We can say gamma. If we have many levels, you have to precise. Maybe you can have gamma 1 or gamma 2 and so on. As we have only one transition, we have only two excited or two states. We can say directly we have only one gamma transition. First of all, you have to know if I have same parity or we have a different parity. If we have same parity, you can write directly this notation. We must have, or the solution must be chosen by M1 or from M1, E2, M3, E4, and so on. So in the case of same parity, you can write M1, E2, M3. Okay, now I know just the starting point. We start by M equals to 1. Okay, and we go up 1, 2, 3, 4, M, E, M, E. If we have a different parity, we start by E. So we have E, M, E, M. When we start by the value L equals to 1, so we have E1, M2, E3, M4. Now, just I know the initial point, but I don't know exactly the values of L. I need to calculate L. To calculate L, for example, if we have same parity, and we have L equals, for example, 2 and 3. In this case, the solution will be E2 and M3. So we have a quadruple electric, or we have an electric quadruple transition, and we have an octuple magnetic transition. For example, in the case of same parity, if we have L equals to 2, we can say we have an electric quadruple parity because we have L equals to 2. If L equals to 1, we have dipole. If L equals to 3, we have octuple. And the same for in the case of different parity. If we have an example of different parity, you can write directly this one. Okay, if you calculate L and L equals, for example, to 3. In this case, we have an electric octuple transition. Okay, you can know directly the answer from this notations. But for me, I need to calculate to prove the solution. Let me start by this simple example. We have the same parity. What is the condition? The condition here, pi initial must be equal to pi final. Okay, for any condition, for the condition of electric or magnetic, pi initial must be equal to pi final. Now I want to study the nature. We can start here. We have the initial spin equals to 1, the final spin equals to O, the initial parity equals to +1, and the final equals to +1. As we have same parity, we come back to this one. We can know that we start by the point M. We have ME, ME. So we have ME, 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 ME. And we start by M1. So we have M1, E2, M3, and so on. Okay, here we have to calculate L. Now, just I know we have M, E, M, E, etc. And we have M1, E2, M3, and E4. I need to calculate L, and here we have the range. It will be between Ji minus Gf and Gi plus Gf. I substitute the value of J initial and J final to calculate L. So L, it will be between 1 and 1. So we have only one solution, L equals to 1. Okay, so okay, so L equals to 1. In general, I know the solution. If L equals to 1, so the answer will be M1. It will be a magnetic dipole transition. But I will prove this result by calculating this relation. In the case of electric, we have pi final or pi initial equals to -1 power L pi initial. And in the case of magnetic transition, here I ask you to find the nature of the transition. Now I know the multipolarity. The multipolarity is dipole, but I don't know if you want. I don't know the nature of the transition. In this case, we have to find electric or magnetic by writing these two relations between pi initial and pi final. In the case of electric, we have pi final equals to -1 power L pi initial. In the case of magnetic, we have pi final equals to -1 power L plus 1 pi initial. In this case, we can substitute the value of L here and here, and we have to validate only the case where pi initial equals to pi final. Okay, we put here L equals to 1, we get finally pi final equals to minus pi initial. It's not valid. So we don't have, you know, here we are studying the electric, so we don't have E1. Okay, so E1 is no, because we get P final equals to minus pi final equals to minus pi initial. But here we have pi final equals to pi initial. We go to the second case, the magnetic transition. Pi final equals to -1 power L plus 1 pi initial. We can substitute the value L equals to 1 here. We get finally pi initial equals to pi final. It's okay. We have a true. We can say yes. Yes for M. So we have here M, L equals to 1. We have M1, but we don't have E1. We have a magnetic dipole transition. We don't have electric dipole transition. Okay. So like this, we have the solution. The solution will be, we have a magnetic type as a multipolarity, no, as a nature, and we have dipole as multipolarity. Here, I ask you to find the multipolarity and the nature of any transition. We go directly to the second example. This example is the case of a same parity. Now we go another example. We have a different parity. You know, in the case of different parity between the initial state and the final state, we have minus and plus. You can say directly, you know the starting point. You start by E. In the case of different parity, you start by E. We have EM, EM, EM. We start by L equals to 1. So we have L1, E1, M2, E3, and so on. Till now, I don't know the values of L. We put L between the limit. We have the lower limit and the higher limit. Okay. I put L. I put I by its value. You get here L will be between 1 and 1. So L equals to 1. You know, you can say directly here L equals to 1. So we have E1. We have an electric dipole transition. Let me prove this result by calculating the electric and magnetic formula. Here we have pi final. I put L equals to 1. In the case of electric transition, we get here pi final equals to minus pi initial. It's true because we have pi final equals to minus pi initial. It's okay. So I can valid E1. Okay, so E1 is okay. But about M1, it's not okay, because if you put L equals to 1 here, you get finally pi initial equals to pi final. It's not valid. So for E1, you can say yes, but for M1, you can say no. So here we have an electric dipole transition. Okay. We go to the third example. Here I give you an example of J initial and J final equals to half and half. So we have here same parity, the condition pi initial equals to plus pi final, and we have initial spin equals to half, and we have final spin equals to half. As we have same parity, you can say directly we have M, we start by M. We have ME, ME, etc. We have M1, E2, M3, E4, like this. Now we have to calculate the value of L. You know, we can put here half minus half and half plus half. We get finally here L is between 0 and 1. You know, the minimum value of L, it must be equal to 1. So here, if L equals to O, we have no radiation. Just for L equals to 1, we have radiation. So we can say directly we have M1, we have a magnetic dipole transition in this case. To prove this result, we go to the electric and magnetic condition. Pi final equals to -1 power 1 pi initial. We get finally here pi final equals to minus pi initial. It's not the case, okay? So it's not valid. We can say here E1, no. What about the magnetic condition? We put here L equals to 1. We get here pi final equals to pi initial. It's okay. So we have M1. Yes. So the answer will be M1. We have a magnetic dipole transition. Okay. Between half and half, half plus and half plus. We go to the next example. Here in this example, we have a different transition between 5/2 minus and 3/2 plus. We can say and follow the same procedure as we have here we have a different parity. You can say directly we have E1, M2, E3, M4, E5, M5. No, we have E, M, E, M, E, M. Okay, like this. We start by 1, 1, 2, 3, 4, 5, 6. Okay, we continue like this. Now we have to find the value of L. If you put here 5/2 minus 3/2 and 5/2 plus 3/2, we get finally here L will be between the minimum limit will be 1 and the maximum limit will be 4. So L equals to 1, 2, 3, 4. These are the values of L. So we can say directly, this is the answer, E1, M2, E3, M4. Okay? You can say directly, but we have to prove by calculating the conditions of E and M. In the case of E, if you put here, look, for each case, I have to put L. You know, here we have L equals to 1, 2, 3, 4. If I put if I put here L equals to 1 and 3 here, we get pi final equals to minus pi initial. So we have the right condition. Okay, we have an opposite condition. So if I put here L equals to 2 and L equals to 4, in this case, we get here pi final equals to plus pi initial. It's not the condition. So here we have only the odd value for L equals to 1 and L equals to 3 will respect the condition. In this case, we have only E1 and E3. But in the opposite case of the magnetic condition, as you know, here we have 1, 2, 3, 4. If I put here L equals to 1 and 3, in this case, we get pi final equals to pi initial, so we cannot respect the condition. Okay, so we don't have here M1 and M3, no transition. In this case, we don't have M1 and M3. If you put here L equals to 4 and L equals to 2, we get pi final equals to minus pi initial. So we respect the condition. In this case, we have M2 and M4. And here we have E1 and E3. In this case, we get the good result will be E1, M2, E1, M2, E3, M4. These are the results. But you have to know always the first two transitions, E1 and M4, are most likely transitions. We have most probability to have E1, M2 than E3 and M4. Here we have a high possibility to have this transition. Here we have a low probability to have E3 and M4. So like this, we have a good idea and we have the answer and all the possibilities of the transitions between these two states. Okay,